Now, when I want to reconstruct, so hopefully now you have understood the fast algorithm. I want to reconstruct. Why do I want to reconstruct? Because I want to obtain approximations or details or components of the signal in a particular frequency band. So, for example, going back to this figure, suppose I want the signal component in the range 0 to omega max over 2, okay, and I do not want any other signal component. Then what I could do is I could take A1 alone and reconstruct the corresponding part. That is what we had denoted as x hat of 1 earlier, x hat 1 of t. And likewise, I may be interested only in the frequency range omega max over 2 to omega max, or omega max over 4 to omega max over 2, and so on, or maybe a certain set of components put together, and so on. This is the basic idea in signal estimation. When I want to do that, I need to know how to reconstruct. Now, suppose I want to recover the entire signal. I have just decomposed. I should be guaranteed that if I don't, if I put together all the coefficients, then I should be able to reconstruct perfectly. Now, one thing that you should remember in decomposition is when I start off with A naught of n and go up to a certain level, let us say I go up to level 2. In a level 2 decomposition, what I would have at the end is A2, D2 and D1. These 3 sets of coefficients are sufficient to completely recover x. I do not need A1. Why? Because A2 and D2 have taken birth from A1. They have the complete information for you to reconstruct A1. So, the way these coefficients are reported by many software packages is A2 is stacked, D2 is stacked next to A2 and D1 is stacked next to D1. Let me just show you that, show that to you on the board. So, if I perform a 2 level decomposition, then I would have coefficients A2, D2 and D1. This is how one would report, of course, as a column vector or a row vector. That convention rests with the software package, but what you should remember is if the signal is of length n, then A2, this sequence here, would be of length n by 4, essentially n by 2 power 2, and D2 would be of length n by 4 and D1 would be of length n by 2. That is a consequence of downsampling. In arriving at D1, we have downsampled once by a factor of 2. In arriving at A2 and D2, we have downsampled twice, because A2 and D2 are coming from A1 alone. Of course, at level 1 I would have A1 and D1, but A2 and D2 are taking birth from A1. And further, if I go down, then A2 would be decomposed. This is called the wavelet tree, DWT tree, and I will obtain A3, D3 and so on. In which case A3 would be of length n by 8, D3 would be of length n by 8 and so on. So, when I report the decomposition, wavelet decomposition at a certain level, if it is a 2 level, I would report A2, D2, D1. If it is a 3 level, I would report A3, D3, D2 and D1 and so on. The total length at any level decomposition will always be equal to the length of the signal, right. That is the basic idea. Now, in perfect reconstruction, what I need to be guaranteed is, let us say I look at a 3 level decomposition. If I take the 3 level decomposition coefficients A3, D3, D2 and D1 and I perform the inverse operation. So, what I have done here is I have convolved and I have downsampled. The inverse operations would also involve some kind of filtering, but it would involve upsampling, right. And there are conditions under which only you can perfectly recover the signal. These conditions are on the filters that are used in reconstructing. That is the basic idea. So, whichever level I start with, the moment I am given all the necessary coefficients, I should be able to recover the signal. That is the condition of perfect reconstruction. I avoid all the theoretical discussion here, but I give you straight away the condition for perfect reconstruction. Assume that this h and g are finite in length. Those who are familiar with signal processing will know that we are referring to FIR filters, finite impulse response filters, because h and g can be also infinite impulse response filters. There has been, we have never imposed such a restriction on h and g anywhere in our discussion until now. But normally the kind of filters that we use in wavelet analysis are FIR filters, and for FIR filters, that is, if I perform my wavelet decomposition with FIR filters, then the synthesis filters will have to bear a certain relation with the analysis filters as given by Smith and Banwell, and in fact, a generalization of this is due to Wetterly. And the derivation of this, the proofs of this statement is given nicely in Mallett's book and elsewhere in literature. I recommend that you look through it if you are really interested. But from a practical viewpoint, what we are interested in knowing is how these synthesis and analysis filters are related, and these expressions are given in 22. H tilde and G tilde are the synthesis filters, and G and H, as we know, are the analysis filters. So, you can see that G of H tilde is dependent on G, that is, the synthesis low pass filter is dependent on the high pass filter, and the synthesis high pass filter is related to the analysis low pass filter. So, synthesis low pass is related to analysis high pass, and synthesis high pass is related to analysis low pass. Although we have been using this term synthesis and analysis, these two sets of filters play dual roles, which means I could consider G tilde, H tilde and G tilde as analysis filters, then H and G become synthesis filters, or I can consider H and G as analysis and G tilde and H tilde become synthesis filters. So, their roles are reversible, pretty much like what we said in frame theory. We talked about frames, and then we talked about dual frames, and we said dual frames and frames can play reverse roles. I can call one frame, fix one as a frame and call the other as a dual frame. When the analysis and synthesis filters are respectively identical, so this condition is for general synthesis and analysis filters, but if I require that G tilde equals G and H tilde equals H, then you can show that these two conditions can be written nicely in the Fourier domain, that is in terms of the frequency response functions, as a single condition given in equation 23. So, now I do not have H tilde and G tilde and H and G separately. The same H and G that I use for analysis will be used for H and G, for synthesis as well. If I do that, what condition should the filter satisfy? Now, we know everything is tied only to one decision, which is that of low pass filter. As long as that low pass filter satisfies this condition. Now, this is a condition that we have seen earlier. If you recall, this is a condition that we had said is required for orthonormality of the scaling functions. Automatically H satisfies this. So, you do not have to really do anything. The moment I choose H that corresponds to a scaling function and essentially satisfying equation 5, then and I design G according to this relation 14, then I have my analysis and synthesis filters already. This 14 comes from the fact, if you recall, that I want orthonormal wavelet basis. So, to summarize, I choose H as a low pass filter satisfying equations 5 and 6, that is the conditions of orthonormality and low pass filter. Then I choose G such that I get orthonormal wavelet basis according to equation 14. Then I can use both these filters for synthesis as well as analysis as well as synthesis. And that is the reason they are also known as conjugate mirror filters. Okay. So, H and G of course are known as conjugate mirror filters, mostly because of equation 14 that we have seen, but these conjugate mirror filters also provide perfect reconstruction. and now we have the reconstruction algorithm at the top. So, there are 3 figures here. At the top we have the perfect reconstruction algorithm, where you read essentially from here left to right. What I am generally given, as you have seen earlier, is an approximation coefficient and all the detail coefficients at that scale and finer scales, right. So, in this algorithm here, I know A2 for example, or this A at the starting A here, and then the D's at this scale, and then the D at the finer scale, and the D at finer scales, and so on. So, if I assume that I performed a level L decomposition, then I have AL, DL, DL minus 1, DL minus 2 up to D1. Right. So, I start with AL and DL upsample. This is intuitively to counter the downsampling operation that I performed, but theoretically you can say that this is to cancel the aliasing. We have not talked about that, but the downsampling introduces some kind of aliasing, and in your reconstruction you have to cancel the aliasing. So, the upsampling cancels that aliasing. So, I obtain the upsampled sequences AL of AL and DL, convolve them with the synthesis filters. As we have just discussed, I can choose the synthesis and analysis filters to be identical, add them up, I recover A L minus 1, and then I have D L minus 1 with me because that is already given to me. Again I upsample them, reconstruct, get A L minus 2, and so on until I reach A naught, which is that I recover the sequence. Now, what I can do is, as I mentioned earlier, I can reconstruct a particular approximation in a particular frequency band, which is that I can take AL alone and upsample, and then that will give me AL minus 1, that is upsample, filter, giving me AL minus 1, again upsample, filter, and so on until I reach the maximum, that is the finest scale. When I perform this operation only on the approximation coefficient in a particular band or coefficients in a particular band, what I recover is the approximation corresponding to that frequency band, or it is the approximation that I have corresponding to that scale, but and that is what it is, essentially big A subscript L, right. And I can apply this as well to the detail coefficients. Take the detail coefficients in any band, upsample, or you can start with DL, upsample, filter, use the high pass synthesis filter, obtain DL minus 1 hat, and so on. Now, I use hats here because ideally to produce AL minus 1, I need both AL and DL. But here what I am doing is I am throwing away the DL, or in other words you can say I am zeroing out the details at level L and only retaining AL. Therefore, I do not get AL minus 1, I get A hat L minus 1. I only get an approximation of AL minus 1. Likewise, here ideally I can take DL minus 1 from what is known to me, but if I do not want that, then I can approximately construct that from DL and so on. So, this is the basic idea in signal estimation. If I want to estimate, if I know that the main component of the signal is in a particular frequency band, I zero out all the other coefficients in all the other bands and then simply perform the reconstruction. So, let us look at 2 examples to conclude the lecture. The first example is more of symbolic, and the second example is more graphical and numerical. So, let us take a signal sequence here of length n, and let us say I want to really perform the DWT or the MRA. Let us choose the Haar filters. The Haar filters are given as 1 over root 2, 1 over root 2, that is a low pass filter, and G of n is the high pass filter, 1 over root 2 minus 1 over root 2. In fact, you can quickly check that when I sum up the coefficients here in h of n, what do I get? I get root 2. So, it satisfies the condition that I had for low pass filtering, right. And in fact, you should check that if I take the Fourier transform of this h of n, it satisfies the condition which is mod h of omega square plus mod of h of omega plus pi square is 2. So, that exercise I leave it to you, and you can also see that the sum of the coefficients of G is 0, which is a requirement for G to be a high pass filter. Remember, G of omega at omega equals 0 is nothing but the sum of the time domain sequence, right. So, therefore, this satisfies all the conditions for generating MRA, for computing DWT using orthonormal wavelets and scaling functions. Okay. So, what I am trying to do here is I am showing you how what kind of results you would get when you walk through the decomposition algorithm at the first step. So, at the first step what you would do is you would take the sequence and perform filtering. Here the filter is 1 over root 2, 1 over root 2. When you perform the convolution, it is essentially taking averages of 2 successive points, because convolution would yield that, right. It is an FIR filter. So, it is performing averaging, but with a factor of root 2 here. That is the A1 tilde that you would get, and this is the D1 tilde which will have successive differences. One, you have averages of 2 successive points, and the other containing differences of 2 successive points. Now, downsample by factor of 2, that is I am going to throw away every other value in my A1 tilde. So, I am going to throw away x2 plus x3 by root 2, I am going to throw away x2 minus x3 by x2 minus x1 by root 2 and so on. And when I do that, I have my A1 and D1, right. Now, quickly what you should notice is, by throwing away a factor of 2, I have not lost any information at all. What do I mean by this? I can start off with A1 and D1 and still perfectly recover my x1, x2, x3 and so on. How do I do that? Pick the first value of A1, x1 plus x2 over root 2, pick the first value of D1, x1 minus x2 over root 2, and then do what? Well, simply perform 2 operations. Take the average, and what would you get? You will get root 2 of x1. If you average the first values in A1 and D1, simply add them up, do not even need to take the average, simply add them up, you will get root 2 x1 divided by root 2. What have we done? In fact, all I need to do is multiply the first coefficient with root 2 in A1 and multiply the first coefficient of D1 with root 2, add them up, I will get x1. What have I done here? I have convolved A1 and D1 with the, in fact, ideally I should be doing upsampling, but I am just saying that I have averaged A1 and D1 with H itself. That means the synthesis filter is also the same. H has coefficients 1 over root 2, 1 over root 2. I take the same coefficients and apply them to A1 and D1. Ideally I should be upsampling also, but I am not showing that operation. So, this is how you can perfectly reconstruct the signal. So, this kind of tells you what you can do. As I said here, you can recover x1, x2 in this fashion and so on. Now, let me show you the second example here on a polynomial that is used in that's used by Mallet in his book, and this signal can also be generated sorry, using Wavelab. In the next lecture, I will show you how to compute this in decomposition and the reconstructions in MATLAB. For now, let us understand this decomposition. What I have taken is, I have taken this piecewise regular polynomial or signal and performed a 3-level decomposition. When I perform 3-level decomposition, I have 4 sets of coefficients A3, D3, D2 and D1. And this plot clearly shows the differing time resolutions. The signal, although being shown continuous, is actually a sampled sequence available, let us say every sampling interval is 1. Then the sampling interval for D1 or the time resolution for D1 will be 2. For D2 it would be 4. For D3 and A3 it would be 8. So, as you can see here, I have 256 points, right. Here, because the sampling interval is 1, the time duration is still 256, but I have 32 points in A3, and I have 32 points in D3, 64 points in D2 and 128 coefficients in D1. Put together the total length is still 256. So, if you are looking at signal compression, for example, you would see clearly that the value of A3 is quite high compared to the values of D1 or D2. So, what I could do is in signal compression, I would say I can store only A3 and D3 and I can discard D1 and D2. Then I would achieve a compression factor of 4, because 32 and 32, 64 coefficients I would store and throw away the other points that I have here, which is 256 minus 64, 192. So, I would have achieved a compression factor of 4. Of course, it would be a lossy compression, but that is the basic idea in the signal compression using wavelets. That is a crude way of compressing, but that is the basic idea. The refinements that you can perform is apply a certain threshold, only store significant coefficients. You do not need to discard an entire level set of coefficients at a certain level. You can apply a threshold at every level and only store the significant coefficients at each level and so on. Those are all the refinements, but that is the basic idea. Now, when you look at the right hand side plot, they are showing the reconstructions corresponding to the coefficients here. So, what we have done here, we have taken A3 and run it through this reconstruction algorithm here. I have taken only A3, upsampled, filtered, again upsampled, filtered and so on, and I would get this big A3, and then I have big D3 corresponding to the small D3. That is, if I were to only use D3 for reconstruction, the small D3, I would recover the big D3. And an important point to keep in mind is the big A's and D's here, the reconstructed components are all at the same time resolution as the original signal. So, you have come back in time fully at the same scale at which the signal is available. What is the difference between then the signal and these components? Well, they contain different frequency components, that is the point, right. And as you can see, the D1 for example here, the reconstructed component in corresponding to D1 contains only the high frequency blurbs, naturally so, because in constructing this big D1 I have only considered the small D1, which is in the highest frequency band omega max over 2 to omega max, and the high frequency bands will contain all the abrupt changes that you see in the signal. The low frequency ones, the slowly changing ones would be contained in the lowest frequency band, that is in small A3 or the component of the signal in big A3. You can see the big A3 is a nicely smoothed version of the signal itself. Now, finally, MRA. In fact, this is not exactly MRA, but in some sense yes, because and in fact I apologize for the ordering here, the ordering is not right here. What is read as A1 here should be A3, and what you see as A3 should be A1. Okay. So, if I take A3, then it is the approximation of the signal at scale 2 power 3 or at level 3. When I add D3 to A3, then I would get the next level approximation, right, and then when I add D2 and D3 and A1, and then I would get the next level approximation which I see here, and when I add all of these, that is A3 plus D3 plus D2 plus D1, then I would get the signal itself. This is possible because I have used perfect reconstruction filters, right. That is what is a condition of perfect reconstruction. I take up all the reconstructed components in the individual bands, add them up, I will recover the signal. So, as I said, the numbering here is wrong. This should have been A3 and then A2, A1, A0. Why the last signal should be called as A0 is because you get the signal back itself, right. So, that is the small error, and we will take note of that when I put up the slides for you. That is it. So, this has been a lengthy lecture of course, but one of the key lectures in DWT, which tells you how the DWT is computed, more importantly how the wavelet filters are designed starting with the scaling functions. Remember we said in CWT that in CWT the scaling functions are derived from wavelets, whereas in DWT we derive the wavelets from the scaling functions, and we generated in particular orthonormal wavelet basis. There exists another route where one can design bi-orthogonal wavelet basis, but we will briefly talk about it in the closing lecture on this unit. And what we have also learned is a pyramidal algorithm and the recursive relations responsible for that fast algorithm, and then went through a couple of examples on decomposition and reconstruction, understanding the results from a DWT analysis. So, hopefully you learned something valuable from this lecture. In the next lecture I will show you how to carry out all of this in MATLAB. Then we will talk about the choice of wavelets and how wavelets are synthesized from the filters themselves. So, that is about it. So, see you in the next lecture.